Hi, this is Mrs. Cribb. This is video 3 for chapter 6, and you need to pull out your notes and get to the acid-base strength portion where we're going to begin learning some more information. Notice that all of these acids listed over here, these are all in your Quizlet. The Quizlet you need to spend a lot of time on strong acids and strong bases. These are the ones you need to memorize. Strong acid give up protons. Remember that a proton is a hydrogen ion, and they give them up easily and ionize completely. These are the strong acids that usually ionize completely. But weak acids do not ionize completely. This is acetic acid or vinegar. Another way of writing this would be HC2H3O2, so that you see the hydrogen in the front of it that it's going to give up. And it doesn't usually ionize all the way. In fact, I can write the equation for this acid. Here would be the acid, and it would give up its one hydrogen ion, that right here. That's where that gives up. And what's left? Well, then you have the C2H3O2, and it lost a positive, so now it's a negative. Because you know, when you lose a positive one, you end up with a negative one. So there's the anion. This would be the anion of the acid, and this is the hydrogen ion of that weak acid, and this is a weak acid. Okay? Now the reason I'm writing it that way is so you'll be able to start associating this weak acid. This is the acid, the A is the anion, the H is the hydrogen that it gives away. All right, now as the conjugate pair of a strong acid or weak base is always weak. So strong acids make weak bases. Strong bases make weak acids. Strong makes weak. The strong acid makes a weak base. The strong base makes a weak acid. So here we have the weak acid, the generic name for it. That A stands for the anion of that acid. That's like this, the anion of the acid, the thing with the negative charge. And of course it's dissolved in water, so that's that pure liquid. And then we end up with its hydrogen ion or hydronium ion, just like up here, and the anion. Now, if I were going to write the equilibrium constant for this, I would write it as the concentration. Remember, equilibrium constants are products over reactants, just like in the previous chapters, products over reactants. So I would write H3O plus, that's the product, times the anion. There's no plus sign in the equilibrium constant, divided by the concentration of HA, which I could put that in blue because we're talking here about the just associated with the reactant side, times the concentration of water. And then we simplify it. And remember that anything with an S or an L, pure liquid, like here, becomes a 1. So what I end up with is just simply H3O plus times the anion concentration divided by the concentration of the acid. That's an equilibrium constant with a special name called the acid ionization constant, the Ka, the acid ionization constant. So we've had the water ionization constant, the acid ionization constant, the equilibrium constant. If you're honors, you had the solubility product constant, and every single one of them are equilibrium constants. They're all this. They just have special names because they're dealing with different elements or different molecules, different reactions. So what about for base? Well, if we have a base, the B for base, and it's dissolved in water, the base always gives away the hydronium ion right here, plus you end up recreating this acid. So for the base, we end up with the hydroxide ion concentration, hydroxide, not hydronium, times the concentration of HB, which would be, this now would be the acid. Remember, the base makes the acid, and the acid makes the base. So divide it by just the concentration of B. Again, the reason is this water goes away because it's a pure liquid. And that's called the base ionization constant, which is just another equilibrium constant. Well, come to find out, if you multiply the Ka by the Kb, you get the Kw. And all of these are just special equilibrium constants. Now we're going to deal mostly with this Ka in our percent dissociation notes. It's something that we're supposed to do. So let me pull up the notes, just one moment. And here they are, the percent dissociation notes. You can use these on the test. So this is a separate sheet that you should print out and take notes on. This one sheet I will allow you to use on the test. So here is the generic formula reaction for an acid. This is the acid, and it makes its hydrogen ion or hydronium ion, because it is in water, and the anion of the acid. Just like here, there's the acid, the acetic acid, there's its hydrogen ion, and there's the negative ion, the anion. So we have HA represents any weak acid, H plus is this hydrogen ion, and A to the -1 is any anion that we're dealing with. Remember, with every percentage, now in percent dissociation, what we're dealing with is something that does not fall apart all the way, like strong acids. Now with every percentage, and this is the percent dissociation formula right here, it's the concentration of the hydrogen ion, this thing right here, divided by the concentration of the original acid, that right there, times 100. All percents are part divided by the whole times 100. We also have to kind of use the Ka formula, the acid dissociation constant formula, which is the hydrogen ion times the anion divided by the acid concentration. So let's just practice a couple bits, and so you can see what I'm talking about, how to use it. It's really not that bad. So here we have a 3 molar concentration. That's the concentration of this weak acid. But we're going to only have 6% dissociation. What is the pH? Okay, remember that pH equals the negative logarithm of the hydronium ion concentration. I've been telling you that's also the same thing as the negative logarithm of the hydrogen ion concentration. So what this is saying is we have this acid that normally falls apart, but only 6% of it falls apart. So if we have a 3 molar solution of the acid, we only get to use 6% of it. So we have to figure out how much that is. So we take 3.0 molar times the percent. But you know, in order to multiply by percentage, you got to turn it into a decimal. So you got to divide by 100. So 6.0 divided by 100 is just 0.06. We use the decimal times 0.06. And that's going to give us the actual molarity, the actual concentration of the hydrogens that we're going to be using to figure out pH. So let me pull up my calculator. And so it's just 3 times 0.06. I get 0.18. Okay, 0.18 molar. That's how much hydrogen ion is. That's the concentration of hydrogen ion. Now all I did was I take the molarity of this acid, this is the acid, but only 6% of it gives me hydrogen ions. So I figure out what is 6% of the molarity. It's 0.18 molar. Now I know what the hydrogen ion concentration is. I can figure out the pH. It's the log of 0.18. Okay, so let's pull this out, or negative log. Negative log of 0.18, close parentheses, enter. The pH is 0.74. 0.74. That's the pH. Okay? 0.74. All right. Now let's try this next question. If you have a 3.6 molar concentration of HF, hydrogen fluoride, only 10% dissociates. What is the pH? So I take the 3.6 molar, I got to multiply it by the percentage. Turn percentage into decimal. So this is going to be 10.0 divided by 100, or 0.100. That's the decimal form. Multiply it by the decimal form. So what do I get then? 3.6 times 0.1. I get 0.36. So 0.36. That's the molarity of this acid. That's how much actually falls apart. It's a not a lot. And so what's the pH? pH equals the negative logarithm of the hydronium ion, or the hydrogen ion. This is the hydrogen ion concentration in this weak acid. So it's the negative logarithm of 0.36. So, scooch this back over. Negative log 0.36, close parentheses. I get 0.44. 0.44. That's the pH. Okay? Alright, so those are pretty easy. And so it's just taking, again, it's just reviewing, take the percentage, multiply it by the molarity to figure out the concentration of the hydrogen ion. Put that into the formula for pH, and you've got the pH. Now let's do this next one, okay? Calculate, this one will be a little bit longer. Calculate the percent dissociation of a weak acid, not acid, in a 0.75 molar HA solution, okay? So, HA is my weak acid. It falls apart into the hydrogen ion and the anion, okay? We have a 0.75 molar solution of that stuff. Okay, this one's going to be a little bit more complicated, so please follow along very carefully. And like I said, you can use this on the test. We don't know, because, okay, we don't know how much I have here. We have an X amount of this and an X amount of that. Because the percent dissociated, it's not going to 100% fall apart. It's going to be partially falling apart. So I can't say it's a 1-to-1 ratio. It's only 1-to-1 if it completely falls apart. It doesn't, so we have to figure this out. So what we can know is what's the Ka. The Ka is always the hydrogen ion times the anion. This is that equilibrium constant over the HA. Okay, so that's a formula we can know. Follow this along very carefully. I gave you the Ka value, and if I do that, that's a clue. You're going to need to use it. So now I'll put the Ka value over here, 1.86 times 10 to the minus 4. And I don't know the hydrogen ion concentration, so I put that in here as a variable, or the anion. So it's X times X over the concentration. Well, I do know the concentration of HA over 0.75. And now my job is to calculate X, because whatever X is the concentration of the hydrogen ion. So I multiply both sides by 0.75. And this is X times X is X squared. Okay? So the 0.75 cancels out there. And now I multiply this times this, and I take the square root. The square root. So this is going to be X. So now I'm going to put this in my calculator. 0.75, enter, times, I got to do it times 1.86 second function, double E, negative 4, enter. That's the value underneath the square root sign, okay? And now I'm just going to take the square root of that, and I always like to go up carrot to the 1/2 power. I don't know why. So at 0.012. 0.012 molar. This is the concentration of the hydrogen. This is the X. The X is the concentration of the hydrogen ion. So now I can figure out all kinds of things. I can figure out the percent dissociation of this. So I'm going to take the percent dissociation is just the, okay, let's go back and look at the formula, okay? It's the hydrogen ion concentration divided by the acid concentration times 100. All right, the hydrogen ion concentration was 0.012. The acid concentration was 0.75, because that's it right here. So times 100. And I'll have the percent dissociation. 0.012 divided by 0.75 times 100. and that's 1.6%. So 1.6%, only 1.6% dissociation. Now, is there anything else I can figure out from this? Well, I can figure out the pH now, because the pH is the negative log of the hydrogen ion concentration. Well, I just calculated the hydrogen ion concentration right here. So it's the negative log of 0.012. I can calculate the pH. Negative log 0.012, close parentheses. 1.9. The pH is 1.9. All right, is there anything else I can calculate here? Well, I know that pH plus pOH is 14. So 1.9 plus the pOH equals 14. So the pOH equals 14 minus 1.9 should be, I'm going to do it on here, 14 minus 1.9, 12.1. That's the pOH. Oh, is there anything else I can calculate? I can calculate the hydroxide ion concentration, because it's the 10 to the negative pOH. So 10 to the negative 12.1. What's that? 10 up caret negative 12.1. I get 7.9 times 10 to the minus 13 is the hydronium ion concentration. See, I can do all kinds of things. Once I know one thing, like the pH, I can do all kinds of things. Okay, please take careful notes with this. And we're going to go back now to the regular notes. All right, here's the regular notes. That's the we added the percent dissociation notes like required. Now we're just going to cover just a little bit more. There's something called amphoteric substances. It's one of the few terms you need to know, and it just means that something can act like an acid and a base. It just depends on what's going on. So here's an example. There's H2PO4. Maybe I should put it in green since it, okay. Here you'll see if you go to the other side, it lost a hydrogen. So it donated a hydrogen. So remember that the hydrogen is a proton, and that acids are proton donors. So that here it's the acid. It donated hydrogen. It went from 2 hydrogens down to 1. So the acid made the conjugate base, and the base made the conjugate acid. So it acted like an acid. Well, what about in this one? Here we have the same molecule, and it's an anion. Notice the negative charge. When you go to the other side, you see it went from 2 hydrogens to 3 hydrogens. So bases are proton acceptors. So in this case, it went from 2 to 3. It accepted a hydrogen, so it acted like a base. So the base made the conjugate acid. The acid makes a conjugate base. So if it can act like both an acid and a base, it's amphoteric. That's all that means. Water is amphoteric. It can do both. Here, water is acting like a base. It's taking the hydrogen away from hydrochloric acid to become, instead of having 2 hydrogens, it now has 3. Water was the acid. It accepted the proton. And hydrochloric acid, of course, was the acid. So water is the base, rather. It accepted the proton. So hydrochloric acid is the acid. It donated the proton, and water was the base. So the acid made the conjugate base, and the base made the conjugate acid. Here, water, this is still H2O. It's a different way of writing it. Well, here, water is going to give this hydrogen to ammonia, and ammonia is going to become ammonium. So it donates a hydrogen, so it's an acid. So the water, when it donates this hydrogen right here, it loses it. This is all that's left. Acid made the base, the conjugate base, and the base made the conjugate acid. So again, water is amphoteric. It can act like an acid or a base. This is just another way of showing you water is acting like a base and acting like an acid. Different ways. So now the last part of this notes is just really easy. Polyprotic. Poly means more than one. Protic refers to protons. So these are protons. Remember that protons are H pluses. So polyprotic means it has more than one H to give away. This one has 2 of them, so it is polyprotic or diprotic to be specific. Here, It's polyprotic or diprotic. It gives away one hydrogen, so now it has one left. And when it does lose that hydrogen, it becomes a -1 charge. Here, this is only has one hydrogen, and it gives away the second one, and now it has a -2 charge. So this is the same substance. First, it gave away the first hydrogen, and then here it gives away the second hydrogen. So it had 2 hydrogens to give away. Now, this one donates one more hydrogen, but this acid is weaker, and the reason is this is the acid, and this is the base. The acid gives away. It's an acid, it's a proton donor, but it's already got a negative charge. Well, what's a proton? An H+. We have a plus and a negative, okay? Opposites attract. So it does not really want to give away this hydrogen, so it's weaker. It takes a lot more work for it to do it. It prefers to keep it. But this one gives away the hydrogen easy. So polyprotic just means it has more than one hydrogen, more than one proton to give away. Diprotic is specific. Now here's just 2 specific ones, 2 protons to give away. Triprotic, 3 protons to give away. Here's a diprotic acid, it has 2 protons. Here's a triprotic acid, it has 3 protons. This triprotic acid could fall apart and become H2PO4 with a -1 charge because that first hydrogen goes away. And then you could take the H2PO4 and it loses another one, has a -2 charge now because another hydrogen goes away because it's and then you could take the HPO4 with a -2 charge. Here's -1. And it could give away its last one and become the phosphate ion, and that's weaker. So the strongest acid would have been here. This would have been the strongest, and this would have been very weak. And notice it gave away 1, 2, 3 hydrogens. Triprotic. Okay, that's the end of this video. Last thing we're going to cover in the next video is titration. See you soon.